Alrighty, here goes nothing. No, I'm not avoiding you. I'm sorry, I took the Thursday off before spring break, and now, it's another B day. If you're listening to this on B day, it's another B day, and I'm not there again. Sorry. Mr. O'Rourke, our principal, asked me and Miss Sherwood to do something today on Wednesday. You might be listening to this on Tuesday, but all of my classes are going to be listening to this on Wednesday. But I'm making a video for Miss Sherwood and I because we are both going to begin observing another teacher in another school. Not that it matters, but that's the details. So this is Unit 11, Lesson 1 notes. It is our last unit of the semester. So yeah, it is probability. So here we go. I'm recording this at 9:18 in the morning, so if I sound groggy or get disoriented, it's because I'm not fully awake yet. But we're gonna make it. So probability. I'm gonna hope that a lot of us know what have a natural sense of what probability is, and I'm gonna hope that a lot of us know about cards. I see some of us with cards in class sometimes. I can think of a couple students that have had cards. So hopefully you know some stuff about cards, but if not, here we go. There's the 52 cards broken down over here on the left. There are 52 cards in a deck. Let's use blue. There are 52 cards in a deck. The deck is broken up into 4 suits, which are the 4 columns there. We've got, in order there as they are given to us, spades, clubs, and then that third column is diamonds, and then that fourth column is hearts. So each suit has, you can look there and count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 cards going down. You've got king, queen, jack, 10 through 2, and then ace. The first are numbered, right? Usually we go, you might play games where ace is the most basic card and that's a 1, or you might play games where it's worth 11 or something like that. So the first few are numbered, 2 through 10. And then the last few, I kind of generalize and call ace a face card. I think I'm wrong. And you can probably, because an ace doesn't have a face on it, like the jack, queen, and king do. But, I don't know. I just kind of lump them together because they have like a design. You know what I mean? They have a design, unlike 2 through 10, where they're just very basic. So I kind of lump it together. So I'm going to say jack, queen, king, and ace. Okay. Probability is a number between 0 and 1 that represents how likely an event will occur. The closer to 1 you are, the more likely it is to occur. Probability is found by doing the following. So desired outcomes over total possible outcomes. So basically, how many times can it happen out of the total, right? How many kings, looking at example A, is it possible to draw? There are only 4 kings in the entire deck out of 52. So the desired outcome, king, there are 4 of them. There are 4 ways that you can draw a king out of a deck. But there are 52 total cards that you could draw. Those are the possible outcomes. So 4 over 52, 1/13. How many red cards are there? Well, diamonds and hearts, there are 26 of them out of the 52 total cards. So that's half. I'm just reducing my fractions there. I'm not going to spend a lot of time on reducing fractions. Numbered card. How many numbered cards are there? Well, that one might take you a minute. You might say 10, right? Because you're like, oh, all the way up to 10. Well, it's 2 through 10. So there are 9 numbered cards in each suit. But if there's 9 numbered cards in each suit, that means there are 36 total numbered cards out of 52. that reduces to 9/13. What's the probability of getting 4? Well, just like kings, there are only 4 fours. Whoops, let's go ahead and erase that. There are 4 fours out of 52, so 1/13. Face cards, and I am including aces again, right? Including aces. Including aces, face cards, jack, queen, king, ace. There are 4 face cards in a suit, but there are 4 suits. So 16 total out of the 52, which reduces to 4/13. And hearts, well, there are 13 of each suit, so there are 13 hearts out of 52, or in other words, 1/4. So probability here is just a fraction, but probability can be written as both a fraction and a decimal. I could actually punch in a 1/13 into my calculator and get a decimal, right? And that's why we say probability is a number between 0 and 1, because in the end, right, a fraction here is between 0 and 1 at the decimal of some kind. So the closer that decimal is to 1, the more likely, right? So the most likely option that we had out of all of these was drawing a numbered card, right? 9/13. That was the most likely. So those are some basic events. Sometimes we specify more than one event. We might ask, what is the probability of A and B? We say this is the intersection. Intersection meaning they overlap. So there's the A events and there's the B events, but what happens when both of them are true? We say and. So there are aces in the deck, looking at example A here. There are aces in the deck, and there are red cards in the deck, but what's the probability of drawing something that is red and an ace? Well, you might like to visualize up here, right? We can see the aces down there at the bottom, but only 2 of them are red. So 2 out of the 52. So 1/26 is our probability there. So the more we specify, the less likely it is, right? 1 out of 26, I mean, our odds of that happening are even less. Ace or, well, let's stick with the ands. So face and spade, well, there's all those face cards, but only, so there's 4 in each suit. Well, that means there's 4 that are spade, right? And if you need to go up and look at it, fine, right? Here's the spades. How many are faces? Well, I'm including aces, so the ace, jack, queen, and king. So 4 of them are faces and spade out of the 52, so 1/13. Heart and black, well, hearts can't be black, so 0 out of 13. Now what about or? Other times we want the probability of A or B. Or does not require both events to be true. To calculate the probability of A or B, you use the following formula. So let's think about this. We've got and versus or. And we want both things to be happening, or we don't care. Or means it could just be an ace. It could just be a red card. But it could be ace and red. That still falls under the or, right? Ace and red means I only want it to be both. Ace or red means it could just be ace, like a spade, right? Ace of spades, or it could just be red, maybe a 10 of hearts. Or it could be an ace and red, right? Or has and inside of it, so to speak. So what is this formula saying? It's saying, okay, what's the probability of it just being an ace? Plus, what's the probability of it being red? But we are going to subtract away when it's ace and red. Now, thinking about that, why is that? Why do we need to do this subtraction, right? Because I just said, like, it could be ace or red, so let's just add up all the options together. Well, included in the probability of being an ace is some of the stuff that's in the probability of red. When I say a probability of being an ace, I'm saying 4 out of 52, right? These 4 aces. But 2 of those aces are red. So then when I go and calculate what's the probability of it being red, well, then I'm counting those 2 cards again. I'm double counting, which is bad. So I have to subtract away where I double counted. If that makes sense, great. If not, maybe rewind and re-listen to my thought process. I'm going to paraphrase it one more time. Inside of ace and inside of red are some of the same options. I can't count the same option twice, so I have to subtract it out. So, what's the probability of being an ace? 4 out of 52. What's the probability of it being red? 26 out of 52. But we're going to subtract away ace and red, which is 2 out of 52. I'm running out of room here. 4 plus 26 is 30, minus 2 is 28 out of 52, which reduces to 7/13. I'm going to take up less room next time. Face or spade. What's the probability of it being a face card? 16 out of 52. What's the probability of it being a spade? 13 out of 52. What's the probability of being face and spade? Well, that's what we calculated over here to the left. 4 out of 52. So 16 plus 13 is 29, minus 4 is 25 out of 52. If you still don't understand the logic of why we're doing the subtraction, just believe it. I mean, it's true. Talk to somebody next to you, maybe. Try to figure it out. You are watching this video in class. Try to logic through that. But this formula is very straightforward. You have 2 unique events. Here, in example F, we find the probability of it being a heart, which is 13 out of 52. And then we add it to the probability of it being black, which is 26 out of 52. And then we subtract away when both are true. Well, here, it can't be heart and black. So we didn't double count, right? The 13 cards here and the 26 cards here are all different. In the 16 cards here and the 13 cards here, some of those 16 cards are these 13 cards. I am counting it twice, which is why I subtract. None of the 13 cards match up with the 26 cards, so there's nothing to subtract. So 29 out of 52. All right, let's keep going. So, and I think it's easier to think about. Or you got to remember, oh, wait, I double counted. I counted that thing twice, so I got to get rid of it. All right, the last unique situation that we're considering here, we have and, or what is called conditional probability. Conditional probability is when I'm giving you a condition. So I'm giving you some sort of circumstance. So the probability of an event occurring given some other event has already occurred. The probability of B given A is found using the following formula. Jeez, do you hear that car? Oh my gosh. What in the world? So find the probability of each given a standard deck of cards. So what is the probability it's a heart given it's red? That's what this notation means. This line here means given. So given it's a red card, what is the probability that it's a heart? So when we say given red, that means I gave you one of these 26 cards. Right? See what I'm saying? So we are no longer considering the 52 cards. We are considering the 26 cards. I'm no longer out of 52. I'm out of 26, right? You did not, if you're handing me the cards, you said, hey, find the probability. You gave me red cards. You did not give me a whole deck of cards. Find the probability that's a heart given it's red. So you gave me red cards. What's the probability it's a heart? Well, there are still, if you gave me 26 red cards, there are still 13 of them that are hearts. So 13 out of 26, or in other words, half. Okay, you gave me only spades. So you didn't give me 52 cards. You didn't give me red cards or black cards. You gave me just a single suit. So there are 13 cards that are spades. How many of them are numbered? 2 through 10. 2, 3, 4, 5, 6, 7, 8, 9, 10. 9 cards out of the 13. You gave me black, so given black, there are 26 cards. How many of them are face cards? Well, when we look at the black cards, I'm including aces again. There's the 2 aces, 1, 2, and then 3, 4, 5, 6, 7, 8. So there are 8 face cards given the black cards. So 8 out of 26 reduces to 4/13. If you don't reduce, you're wrong. Okay, so before we dive into what is called two-way tables, let's just think about what we've got. Probability is the chances of something happening. You're always thinking, how many ways can it happen out of the total ways it can happen? At the very start, you're like, oh, probability is easy, right? How many ways can it happen out of the total? Well, if there's only 52 cards, right? There's either 4 kings out of the 52. There's either 4 tens out of the 52. How many out of the 52? But then we spice it up and go, oh, but I don't just want tens. I want tens that are red, right? So then your options become smaller when we say and. Our options become bigger when we say or. They could be tens or they could be red, right? So there's all these red cards and there's all these tens, right? It could be any of them. That would be or. And then conditional probability, okay, I'm giving you some cards, but not all of them. So let's get away from cards, and because cards can only take us so far, probability becomes more interesting when we think about like some real life things, I suppose. Two-way tables organize data based on 2 categorical variables. Two-way frequency tables show how many data points fit into each category. A two-way table is a way to display frequencies or relative frequencies for 2 categorical variables. One category is represented by rows, and all right. Let's just dive in and look at it. So look at the way this thing is split up here. We are talking about foreign languages or not taking foreign languages, sport or not a sport. All these two-way tables, as it says here, 2 categorical variables. It's either they sport or not a sport. Foreign language, not a foreign language. Yes or no. It always boils down to yes or no. Yes, they took a sport. No, they didn't take a sport. Yes, they took a foreign language. No, they didn't take a foreign language. Yes, the plane arrived on time. No, the plane didn't arrive on time. Yes, I've been to Canada. No, I haven't been to Canada. Yes, I have flip-flops. No, don't have flip-flops. All right, it could be anything, but it boils down to yes or no. So we can look at this table and we can like see out of the total number of people, which is 50, right? If we can add up these rows or these columns and say 14 plus 10, 24 played a sport. 14 of the 20 out of the 24 who played a sport, 14 of them took a foreign language, 10 did not. Or we can look at this column. Oh, there are 26 people total here in this column, so 26 did not play a sport, 3 of which didn't take a foreign language, 26 did. Right? So it's this nice way of like breaking down all of the different possibilities. We're not missing anyone here, right? There's no like, oh, they took a sport and a foreign language. Yeah, it's right here. They took a sport and didn't take a foreign language. Oh, yeah, it's right here, right? We've met every single possibility there. So let's fill in one on our own here. 360 people were surveyed. All right, boom, that instantly goes into total. Fill in the easy stuff. Boom, that instantly goes into our total of totals. 360 people were surveyed about their travels to Canada and Mexico. 5/12 said they had been to both. All right, break out the calculator. What is 5/12 of 360? I have a calculator in my hand. I'm doing 360 times 5 divided by 12. I get 150. So 5/12 is 150. 150 said they had been to both. Where does that go? have been to Canada, have been to Mexico. They have been to both things. That goes in this box. 1/4 said they had not been to Mexico. 1/4 of 360, that's easier. That's 90. 90 said they had not been to Mexico. Okay, what does that mean? Here's not been to Mexico. That's how many total people have not been to Mexico. That goes in the total box, right? Of those 90 people, they still could have gone to Canada. Right? So that goes over here on the far end on the right. 7/12 said they had been to Canada. All right. I don't know what that is. So 360. I'm taking 7/12 of 360, by the way, right? We're talking about the total. So 7/12 of 360 times 7 divided by 12. That's 210. 210 have been to Canada. Again, that's a total. And that's all they gave us. But that's all we need. If 210 have been to Canada in total and 150 did both, that means the remaining people, 60, have not been to Mexico. Okay, well, 90 people have not been to Mexico, 60 of which have been to Canada. Well, then that means 30 have not been to Canada either. Well, if 360 people total were surveyed and 90 of which have not been to Mexico, well, then that means everyone else has been to Mexico. You either have or you haven't. So 270 have been to Mexico. Well, if 270 people have been to Mexico and 150 of them have been to Canada, the remaining people have not been to Canada. So 120. And if 120 people have been to Mexico that have not been to Canada, and 30 have not been to Canada or Mexico, well, in total here, 150 have not been to Canada. It's just breaking it up into these possibilities. We're not leaving anyone out. And all of these columns and rows should add up nicely. 150 plus 120 is 270. Check. 60 plus 30 is 90. Check. 210 plus 150 is 360. Yes. 150 plus 60 is 210. Yes. 120 plus 30 is 150. Yes. 270 plus 90 is 360. Yes. So, let's answer these questions. How many people were surveyed? Easy, 360. How many people went to Mexico? Well, look at this. The table, like the tables are your friends. You might find yourself wanting to make a table all the time. I know I do. It's just this nice, easy representation of all the data. So who has been to Mexico? Here's the been to Mexico column. Look at the total, right? Some of the people who have been to Mexico have not been to Canada. I'm not concerned about that. I'm concerned about how many people have been to Mexico. 270. How many people went to Mexico but not Canada? Well, where do they intersect, right? Here is has been to Mexico, and here's not Canada. So where the two intersect is at 120. How many people have been to both? Well, has been to Canada, has been to Mexico. Where do they intersect? Right there at 150. How many people have not been to Canada? As a total, here's the not been to Canada section, 150 total. How many people have not gone to either? Well, not Mexico, not Canada, overlap at the 30. Now, what's very nice about these two-way tables is that it makes questions G, H, and I really easy to think about. So what does this notation mean again? It says, given they have not been to Canada. That's what this is saying. So how many people have been to Mexico that have not, what's the probability of you choosing someone that's been to Mexico, given they have not been to Canada. So going back to the cards, we were thinking, oh, if you gave me red, that means I'm only looking at the red cards. Well, you're giving me people that have not been to Canada. Right? We are giving folks that have not been to Canada. So we are now out of 150, right? Whoops, I didn't write very well. What the? 150. So I'm no longer considering the 360 people that were surveyed. I'm considering the people that have not been to Canada, which is 150. All right. So of the 150, how many people have been to Mexico? 120. This is not asking you for the probability of people who have been to Mexico, right? There's 270 people that have been to Mexico. I want the people, given these 150 people that have not been to Canada, how many have been to Mexico? 120, which reduces down to, they're both divisible by 30, so 4/5. All right, so given they've been to Mexico, all right, now we're looking at the 270 people, right? There are 270 people that have been to Mexico. So given those 270, what's the probability they have not been to Canada? 120. Right? Not Canada is this 120. 150 have been, 120 have not been. Those are both divisible by 30 again, right? That is 4/9. Probability they've been to Canada given they have not been to Mexico. So we look at the not Mexico section and we say, oh, we're out of 90 now. How many people have been to Canada? 60 of the 90, which reduces to 2/3. So this two-way table, it gives us all these totals. It gives us this nice representation of all the different total possibilities. All right, let's keep doing some tables here. Let's come up with our categories, right? I gave you the not Mexico, Mexico, not Canada, Canada. Let's figure out what our categories are here. How long has this been going, by the way? We are up to 27 minutes. Whew. All right. As each person entered the theater, Aaron counted how many of the 105 people had popcorn and how many had a drink. All right, I already know what the categories are. Do you? Popcorn, not popcorn. Drink, not a drink. Right? When they walk into the theater, they either have popcorn or they don't. When they're walking into the theater, they have drinks or they don't. So, popcorn, no popcorn. Drinks, no drinks. So, of the 105 people, boom, I have a total. How many had a drink? Aaron counted how many? Okay, he found that 84 people. He found that out of 84 people that had popcorn, only 10 did not have a drink. All right, what did we just answer? He found that out of 84 people that had popcorn, he just told us how many people had popcorn right there. We're kind of phrasing it, we're saying such a long sentence. He found that out of 84 people that had popcorn, only 10 did not have a drink. But inside of that sentence, we were told two things. We were told the total number of people that had popcorn, 84. And of those 84, 10 did not have a drink. Not 10 people total didn't have a drink. But of these 84 people, 10 of them did not have a drink. Looks like 16. 10 of them did not have a drink. Meaning 74 did, right? Of the people that had popcorn, this is the people that have had popcorn, right? They have popcorn. Well, 10 of them didn't have a drink and 74 did. 6 people walked in without a drink or popcorn. So where does that go? Right there. So we can fill in everything now. If we know there are 105 total people and 84 of them had popcorn, 105 minus 84 is 21. I don't know why I used the calculator. If 21 people didn't eat popcorn, well, 6 didn't have a drink or popcorn. So some people just got a drink. And that would be 15 people. 15 plus 6 is 21. So now we have these individual totals. Well, in totality, how many did not have a drink? 10 plus 6, 16. How many people did have a drink? 74 plus 15, that is 89. And you can go back through and double, triple check and make sure everything adds up correctly. And I would recommend it. I'd recommend going, does 89 plus 16 add to 105? Yes. Does 84 plus 21 add to 105? Yes. So on and so forth. So what's the probability of grabbing popcorn? Well, how many people had popcorn? 84 out of how many total? 105. Easy. How many people had a drink? Well, go to that total column, and here's drinks. 89 had a drink out of 105. How many people had a drink and popcorn? Well, where do they overlap? Drink, popcorn, 74 out of the 105. Drink or popcorn. Now, we were subtracting the overlap, but in a two-way table, we can see all of the drink or popcorn situations. Tell me, which is the only one that's not included? If it's drink or popcorn, the only little box that's not included is, wait for it, which one is not included? Right, here's all the people. Here are all the possibilities. Right? These numbers all add up to 105, right? These are the 105 people right here. 74 plus 15 plus 10 plus 6. These are the 105 people. Which people wouldn't fall under drink or popcorn? These fools who didn't get anything. Right? So add up this thing, and this thing, and we got it all. 10 plus 74 plus 15 all over the 105. Which is, so don't screw this up, 10 plus 74, whoops, not 1,074. 10 plus 74 plus 15 is 99 out of the 105. That looks like a 2. So, you see what I'm saying there? I think the two-way table makes these all so much easier, right? Drink or popcorn, we'll just add up all the ones that involve drink and popcorn, aka the only one you're leaving out is the 6. They don't have drinks or popcorn. What's the probability they have a drink given they have popcorn? Okay, well, given they have popcorn means I'm only looking at these 84 people. So of those 84 people, how many had a drink? 74. What does this mean again? It means and. That is intersection. If you see an upwards U, that means or. If you see whatever that is, that means and. Okay? So, no drink and no popcorn? Oh, that's easy. The 6 people out of the 105. No drink, given no popcorn. All right, so how many people didn't get popcorn? 21. So of those 21 people, how many people didn't get a drink? These 6 people. 6 out of 21. Two-way table is your friend. Oh my gosh, it's your friend. It just spells it out for you. Like all of the numbers are here. Like literally, did you realize we didn't do any calculation here? Right? Once you fill in that lovely two-way table, it's just read it. You need to be able to read the two-way table that you have created. And that is some of the struggle for some of us is we don't know how to read it. The columns tell us certain things. How many people had popcorn? 84. How many people didn't have popcorn? 21. But then of those 84 people, it gets split into people who had drinks and didn't have drinks, right? So these are the totals, but these are the individual situations in the center. Those are of the utmost importance, right? Those are the things that matter. These are the 105 people right here. We're looking at them. So know who they are. Popcorn and drink. Popcorn, no drink. No popcorn and a drink. No popcorn, no drink. All right. Let's make our own table from absolute scratch. 180 students were surveyed if they watch DC and Marvel movies. So let's make a table. Boom, 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 boom. So it's whether you watch DC or not, whether you watch Marvel or not. So DC, no DC. Marvel, no Marvel. 180 students were surveyed. Boom. 180 students were surveyed if they watched DC and Marvel movies. 68 said they watched DC. Okay, perfect. That's a plain as day number. 68 said they watched DC. All right. Actually, let's do some colors here. 68 said they watch DC. Less than 1/11th said they only watch DC. What does that mean? Less than 1/11th. Well, what is 1/11th? Well, let's break that down. 1/11th of 180 is equal to 180 divided by 11 is 16.36. You can't have 16.36 people. So it said less than 1/11th. Less than 1/11th of 180 would actually be equal to like 16, right? 16 or lower, 16 or less. It could literally be 0 people. It said less. I mean, I know that sounds stupid, right? Well, but why wouldn't you say 0? That's because the answer isn't 0, right? But it says less than 1/11th, so 16 or less said they only watch DC. So where would that go? Think about where that would go. Only DC. Here's the DC people. Only meaning they don't watch Marvel. So this is 16 or less. Let me actually zoom in and write that again. Come on. There we go. 16 or less. Okay? More than 4/7, more meaning greater than, and let's change colors. Let's do red. More than 4/7 of 180. Well, 4/7 of 180 is, oh, my phone's gonna die and I'm not gonna have a freaking calculator. 180 times 4 divided by 7 is 102.86. Well, again, I can't have 102.86 people, so 103 or more. So where does that go? Let me read that again. More than 4/7 said they only watch Marvel movies. Only watch Marvel, meaning Marvel and no DC. So that would go here, 103 or more. Yeah? So more than 4/7 said they watch Marvel movies. What is the greatest possible amount who watch neither DC nor Marvel movies? So who are the weirdos? No offense. Just kidding. You're not a weirdo for not watching superhero movies. In fact, I applaud you. What is the greatest possible number that can go here? All right? No DC, no Marvel. We need to use the table to our advantage here. Because how does the math work out, right? Like, if 68 people only watch DC, well, what does that mean? That means 112 don't watch DC. So this column right here is so important for us, but especially that box right there. Why is this column so important? Because, well, it's the one that involves this box here, and we know we have a total. I don't know really anything about Marvel totals, right? I know everything about the DC totals, but these Marvel totals, because I don't have any specific numbers, I literally don't know anything about the total people who watch Marvel don't. What I do know is how many people watch DC and do not. So, so this red part here, 103 or more, is important to us. So it said 4/7 only watch Marvel movies, which was the 103. More than 4/7 watch only Marvel. So that means these folks are here. This total affects this total, right? Because in the end, it's got to add to 112. So I want you to, it says more than 4/7. I keep going back and forth. Hopefully you see where this is already going. 103 or more. The bigger this number gets, the what this number gets. If this number is getting bigger, this number here that we care about is getting smaller. Because in the end, it's restricted. It's got to add to 112. If 111, because it says 103 or more. Well, if 111 watch only Marvel, well, that means only one person could be in that box, right? And what is the question asking? What is the greatest possible amount? Well, that means we want to maximize this number. We don't want to make it smaller. We want to make it bigger. So what number should go here? 103, the smallest possible number. 102 is too small, right? Because it has to be greater than 4/7. 102 would be slightly less. So we had to choose 103. So if we make this number literally 103, well, then that means this number is 9. So our answer is 9 people. Are you with me on that? Your final exam is the EOC. If you are unaware, you are now aware. The final exam is the EOC for this semester, the end of course assessment, the state required test that all of us have to take, okay? Probability is on the final, and there is like a question, there are questions that are like this, right? I'm not saying there's a question exactly like this because, we don't see the test until we hand it to you. It's a top secret test, right? So what I'm saying is that there are questions that are difficult like this. We've seen practice problems and such, right? You can go look up practice problems for, exams and whatnot. There are questions similar to this, which is why I'm writing a question like this, right? This is not just something I pulled out off the internet, right? I wrote this question so that to gear it towards those more difficult questions on the test. All right, let's do one more. What's our time at? 43 minutes. Okay. We're good. Students are asked if they own an Android or iPhone. The probability they own an Android is 0.35. The probability they own an iPhone is 0.65. Oops. The probability they own both is 0.05. If one student is selected at random, and we already know they own an Android, what is the probability they also own an iPhone? When I read that, all those words, I don't friggin' know what I just read. I'm going to make a table. Like, literally. I'm always making tables. Now, sometimes the question doesn't lend itself to a table, right? If there's like more than two situations, right? This is iPhone, Android, or DC, Marvel, right? If they're giving you all these other things like blue and green and red and green marbles and stuff, yeah, the two-way table is not going to work out. But lots of times it does come down to like one or the other, right? That's how lots of surveys are done, right? This or that. So lots of times two-way tables are going to lend themselves to be really useful. Something to point out, and the reason why I made this question star, 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 is that two-way tables do not necessarily have to be the literal number of people, right? This is not telling me the literal number of people. It's telling me the probability. And that is totally fine. Two-way tables can literally just be probability. So what's the total? 1, right? Probability can get as high as 1. So let's get our categories first. Android, no Android. iPhone, no iPhone. So probability can get all the way up to 1. You can't be more than 100%, right? It's not possible. So 1. So the probability they own an iPhone is 0.65. That is the total. Like, of all the people that were surveyed, the probability that they own an iPhone is 0.65. So 0.65 is our total, right? That's the total probability, so to speak, for iPhone users. The probability they own both, okay, iPhone, Android, is 0.05. Oh, I skipped that first line, whoops. The probability they own an Android is 0.35. So if they own an Android, it's 0.35. So the people who don't own Androids are 0.65. And this is 0.35. So the probability they own an iPhone is 0.65. The probability they own both is 0.5. If one is student selected at random and we already know they own an Android, what is the probability they also own an iPhone? So we already know they own an Android. Oh, we're out of 0.35 now. Yeah? What is the probability they own an Android? We're out of 0.35. We're no longer out of the total 1. We're out of the 0.35 people who own an Android. So of those people, what's the probability they also own an iPhone? Oh, so that's 0.05. So of these, how many people own an iPhone? 0.05. And 0.05 divided by 0.35 is 0.05 divided by 0.35 is 0.14. Boom. And again, I don't think when I read that, I know I said this at the start, and I'm saying it again at the end. When I read this problem, I'm like, how am I supposed to answer that, right? I don't have like when it says of the people who own an Android, what does that mean, right? I mean, I know it told me this sentence, but when I see it in a table and I can visualize the totals, then of people who own an Android makes more sense to me because I can see the totals and how they match up, you know? So make tables. Highly suggest it. This problem is something like I said, that we will see on the final exam. You might rewind and re-listen to some of my logic for this problem, okay? You just might do that. I highly suggest it. That you will see this problem again. I mean, especially like at least on my test, right? I'm writing the test for this. You're gonna see this problem. Sorry. And it's difficult. This whole less than, greater than. Go back, re-listen to that. All right, we did it. Congratulations. You will, just to kind of conclude here, you will have these things, whether it's written on the board or given to you on an equation sheet or something. I myself don't always have these memorized, so I don't expect you to. Especially, we only have 2 lessons of this unit. You don't have a lot of time to memorize it. So you will be handed those things, but be comfortable using them. I don't think you're going to look at this and go, well, I know what that means, unless you have done the practice problems and you're getting comfortable and you've asked me questions, okay? So come to class with some questions, right? I'm going to see you, my B-Day folks. You're watching this on Wednesday because we have a double A day this week, Monday, Tuesday, because of the snow makeup. So you're watching this on Wednesday. So I want you to ask questions on Friday, please. our lesson, I believe, is not as long on Friday, so we will have plenty of time to ask questions. Please come with questions. Please do the practice. A lot of this is quick. These problems are quick. And or the two-week tables take some time to create. I mean, duh, right? There's a lot of numbers, but get used to reading them. Get used to making these categories. All right, I'm done sharing my wise words. Do the practice, please. Have a good one, both Miss Sherwood kids and my kids. All right, see you later. Bye bye.